Okay, as I mentioned in the beginning of the class that before this, we talk about the forward and the inverse kinematic. The forward and inverse kinematic that we derive are derived based on the assumption that we don't have the motion on the robot. Everything is considered in the static case. And what if we want to find the relationship between the joint velocity and the velocity at the endpoint and the rate of change in the orientation at the endpoint. So the main topic for today, we are talking about the differential motion, I'm not sure we can cover these three parts, or maybe if the time's up, we may can complete only the two first part. Let's see. We have the differential relationship. What is the differential relationship? This is a planar two-arm revolute manipulator. I hope you still can remember the forward kinematic to this robot. The x position is a function of the θ1 and the θ2, right? X is L1 cosine θ1 plus L2 cosine θ1 plus θ2. And the y coordinate is L1 sine and L2 sine. X and y are measured with respect to the global frame. And this is the xy position of the origin of the endpoint frame. And yes, θ1, we have θ1 and θ2, and we have the length of the arm. For this, we can obtain from the forward kinematic. For the differential relationship, the meaning of the differential relationship is what should be the infinitesimal change of the x position. What should be the small change of the x position? It should equal to the change of x against θ1 and the small change, infinitesimal change of the θ1 in combination with the change of x against θ2 with the small change of θ2. And similarly, in the same way, the small displacement, the small position change of the y x, the small change of y curve y by curve θ1 d θ1 and curve y by θ2 d θ2. If we write this in the metric form, dx and dy is equal to curl x by curl theta 1 and curl x by curl theta 2 d theta 1 d theta 2. So dx is equal to curl x by curl theta 1 d theta 1 plus curl x by curl theta 2 d theta 2 from the first relationship. For the second relationship, dy is curl y by curl theta 1 and curl y by curl theta 2. So this is Jacobian metric. Jacobian metric. Jacobian metric describe the relationship between the endpoint coordinate and each joint coordinate, endpoint coordinate, joint coordinate, endpoint coordinate, and joint coordinate. And yeah, let's try to if we check this is example, if we check this as example, what should be the Jacobian metric? What should be the Jacobian metric of this robot? Curl x by curl theta 1, curl x by curl theta 1 is the dip of x by d theta 1 when we consider theta 2 as constant. Curl x by curl theta 1, L cos will be dip cos will be psi, and this also dip cos will be psi. By the way, we need to dip of theta 1 plus theta 2 by theta 1, right? But if we use the curl operation, it means theta 2 is a constant, So d theta 1 by d theta 1 is equal to 1. So this term equal to 1. The whole term equal to 1. This is the first component here. The second component is dip of x by theta 2. The first term, we have L1 cosine theta 1. We need to consider this one as constant. So dip of constant is equal to 0. Dip of this term by theta 2, dip cos is minus psi. What? Oh, I'm sorry. Dip cos is minus psi. Dip cos is minus psi. Dip x by theta 2, the first term, dip constant is 0. The second term, minus L2 psi. And yeah, dip of theta 1 plus theta 2 by theta 2. Theta 1 is constant, so it will be 1. How about dip y? Curl y by theta 1. Curl y by theta 1. Dip psi is cos. This side is cos. And curve y by theta 2. So this is Jacobian metric. This is Jacobian metric. We may try to write the metric equation. The metric equation, this one. Jacobian and d theta. So the metric equation if we take the time derivative, the relationship between infinitesimal position change and joint angle change are related with the Jacobian. We also can relate the velocity and the joint velocity. Yeah, how can we write this in the metric? It seems to be we have dx by dt and dy by dt. Jacobian still be the same one. No. Jacobian still be the same. Jacobian the same. And the joint velocity. The first column, the second column of Jacobian, if we name it as a vector J1, J2, if we name it as a vector J1, J2, the vector J1 relate the endpoint velocity as a function of the velocity of joint 1. J2 relate the velocity as a function of the joint velocity 2. We can like dx by dt and dy by dt. If we separate the J1 and J2, the J1, I'm sorry. The J1 is just consider the change in theta 1. And for J2, we just consider the change of theta 2, the velocity of theta 2. If we name this as J1 and J2, so maybe yeah, the metric we may can say that the velocity vector is J1 vector multiplied by J1 vector multiplied by the theta 1 dot and J2 theta 2 dot. Okay, check this from the textbook. I hope, yeah, you can read the book, and when you make a summary of the book, I think you can have the same with me. But in the books we have like the extensive explanation. Someone will like it, maybe someone don't like it, don't want to read the long context. So infinitesimal rotation. I hope we still remember how to obtain the rotation metric when we consider the rotation about an axis. But before this, we have delta of the theta. I mean, the rotation is rotated with the finite angle, but in this case, it's infinitesimal angle, a very, very small angle. We have one advantage from the rotation about a small angle, about x, y, and z axis. The major advantage is that for a finite rotation, the order of rotation is important. If we switch the order of rotation, if we rotate about x, then rotate about y, then rotate about z. If we rotate with this order, and if we rotate with the different order, x, y, z, we have different results about the rotation. But for the small rotation, we can switch the order of rotation, and it's not affect the total, the final solution. So I want to remind you about the rotation metric. The rotation metric, when the angle, when the axis change, it is composed from the dot product of the new axis x and with respect to x, y, z of the original one in the first column. In the second column, the new y-axis, make with the original x, original y, original z axis. Yeah, we can set the unit vector for it. The dot product. And the z axis make with original x, original y, and original z. This is how we compose the rotation metric. So let's review the idea. We have this x, y, and z. If we rotate about x with a very small angle, we're gonna change y direction to y prime, and we're gonna change the z to z prime. And the angle will be the small angle. Let's compose the rotation metric. X and x prime has the same direction. Cosine 0 x dot x prime dot x is magnitude of x prime, magnitude of x cosine theta. The theta is the angle between the two vectors. The magnitude of unit vector equal to 1, right? This is the angle between the axis. So this, it has the same angle, cosine 0 equal to 1. X prime make 90 degree with y and make 90 degree with c. So cosine 90, 0 and 0. How about y prime? Y prime make 90 degree with x. Y prime with y. Y prime with y. Cosine d theta x. And y prime with c. Y prime and c. This angle will be 90 degree. So cosine of this angle will be sine of this angle. How about C prime? C prime have 90 degree with x. C prime and y. We have this 90 degree plus this. So the angle will be cosine of 90 degree plus d phi x. So cosine of 90 degree plus d phi x. Cosine will be the value in the x axis. So it will be minus sine of d phi x. How about z prime and z? We have cosine of d phi. If the angle is very small, what happened to the sine and cosine? What happened to sine and cosine? Cosine of a very small angle can be estimate to be 1. Sine of that angle can be estimated to be that angle measured in radian. Sine can be estimated as that angle measured in radian. Cosine of near zero is cosine 0 equal to 1. This is the rotation about the x-axis. If you try to check, yeah, I should write this is the rotation metric about x with the angle d phi x. If you try to use the same concept to compose rotation metric about y with angle d phi y. Use the same idea. You can obtain this metric. You will check by yourself. What can we see from here? What can we see from here? I want you to check. I want you to check what is the product. What is the product of rotating about x, then rotate about y with the small angle, rotate about y. So we are going to find the product of the metric, Let's continue in the next page so that we have enough space. We have the rotation metric about x, this one. We have the rotation metric about y with more angle. So the rotation metric about x and rotation metric about y. The rotation metric about x with the small angle. We have 1, 0, 0, 0, 0, and 1, and d phi x minus d phi x and 1 for the x. And for y, we have 1, 1, 1, and minus d phi y and d phi y. Okay, let's compute the product of the metric. This row, first row to first column have 1. First row to second column has 0. First row to third column has d phi y. Second row to first column have d phi x, d phi y. d phi x, d phi y. Second row, second column has only 1. Second row, third column has minus d phi x. And the third row with first column minus d phi y. Third row, second column, d phi x. And 1. Just only one thing special here. Is near zero can be assumed to be 0. Yes. So now we have this. You may try to use the same method to check by yourself. You may try to use the same method to check by yourself for this one. Change the order of the rotation. Change the order of the rotation. So the rotation metric about the y, d phi y. The rotation metric about x with d phi x. If we change the order, we have y, and then we have x. Finally, we should have the same result if you obtain the metric product. Just only one conclusion to this is for the infinitesimal rotation, the rotation metric is not dependent, it is independent to the order of the rotation. You can rotate x, then rotate y, or you can rotate y before rotate x. The metric product with the small angle estimation, the metric product will equal. This is just only one property. We have another one which is useful, very useful. In this step, we have the product of two metrics, x and y, or y and x. If we have the product of three metrics, we have rotation about x with d phi x, about y with d phi y, and about the c-axis with d phi c. With this order, we can switch the order between the order. The switch is applicable. We're gonna have the same product of these three metrics. We're gonna have the same product of these three metrics. How about this? We may multiply it with the change about x, the rotate about x with the different angle, As I mentioned, we can change the order. Maybe for this, you may rotate about the z-axis first with this different angle. And then you rotate about y-axis with one different angle. We can switch the order. It doesn't change the product of these three metrics. We can switch the order. But what can we see when we multiply the two rotation metrics? That is the effect of rotation about x, y, z. Maybe rotation about y, z, x, or z, x, y, not depend on the order. But the important is the angle that it rotates about that axis. What we can see is finally the rotation metric. Finally, what we have is equivalent to the product of metric that rotating about x with the first rotation continued by the second rotation, then multiply by the rotation metric about y with the angle about the first rotation plus the second angle, and rotation about c with the phi, and the another d phi about c axis. What they prove is for infinitesimal rotation, we have one property named additive property. So rotation resulting from arbitrary infinitesimal rotation is given by algebraic sum of the individual component for each axis. From individual component means d phi x prime, maybe d phi x prime if we have another rotation, but about the same axis, we just need the algebraic sum, and we have the additive property. Do you familiar with additive property? I mean, we familiar with the additive property in vector. You can sum. If you remember maybe the position vector. The position vector is equal to maybe x1 plus x2 I plus y1 plus y2j plus y plus c1 plus c2, maybe plus c3 in k direction. So yeah, for infinitesimal rotation, is vector and relate to the direction that it rotates about, and the infinitesimal rotation can be sum. They have the additive property. So you may try to compare the effect of rotation if the angle is delta phi x, delta phi y, delta phi c. We cannot do like this. It's finite rotation. For finite rotation, the order of rotation is important, and we don't have the additive property. We cannot sum the finite rotation as vector. Okay, the third topic for today is Jacobian of manipulator. Before this, in this slide, here we can see the relationship between the endpoint displacement, the infinitesimal displacement, and the velocity, and the joint velocity. So it means that the position, if we write down the position, dp, p is a vector, but we not only consider the position at the endpoint, but we also consider the rotation at the endpoint. This is 6x1 vector, 6x1 vector. For the velocity, is the dip of the vector, position vector by dt, dip of the position vector by dt. We dip the position, we dip the orientation vector by dt. The position vector, this is 3x1, this is 3x1, and the total we have 6x1 vector. If we write the equation, the velocity, endpoint velocity, is related to the joint velocity. Endpoint velocity is related to joint velocity by Jacobian metric. The endpoint velocity has position and orientation, and yeah, you can use the symbol like velocity of the endpoint and omega of the endpoint, but please keep in mind that velocity is a vector. We have Vx, Vy, Vc, and the omega, we also have the omega of the endpoint about the x-axis, about the y, and about the z-axis. And the total dimension of the vector is 6x1. How about this? Joint velocity. What is the joint velocity? Joint velocity is also a vector. A vector contains n component. N don't need to be 6. N don't need to be 6. N depends on how many degrees of freedom of the robot, how many links of the robot. We have the joint velocity of first joint until joint n. And the dimension of the vector will be n by 1. In your own robot, if you have 4 motors, n will be 4. But for the endpoint position, endpoint orientation, we have 6 degrees of freedom. And this don't need to be just a theta. Don't need to be just a theta. It can be the joint offset. If the joint is prismatic joint. So in this topic, we will see the Jacobian metric that relate to the different type of joint, the revolute joint and prismatic joint. Again, if you see here, the Jacobian relate the endpoint position and orientation. J with subscript L means linear position. A means angular position. So if you see this, the joint, let me check. Okay, the Jacobian, sorry. Jacobian is a big metric. The JL1 here relate the endpoint position, the linear position, to the first joint variable, and the metric that relate three position in IJK, the vector has the dimension of 3 by 1. For the orientation, we also has 3 by 1 vector that describe the orientation. But how many vector in the Jacobian? For the linear, we need to create the Jacobian vector that correspond to n joint of robot. Or vector has the same dimension. For the angular position, we also need to formulate the Jacobian that relate to n joint. So finally, the dimension of the Jacobian depends on the number of joint, n, and the dimension of the metric, the full metric, will be 6 by n joint. To give you one clear, to make it clear, hey, what should be this one? What is the 3 by 1 vector that relate the linear position of the endpoint as a function of the chain in the first angle, the orientation of the first angle. Let's see this equation. I'm gonna write, hey, velocity vector at the endpoint, just only this, okay? Velocity at the endpoint, we can form it as maybe Vx Vy and Vc, we can form it. And it's gonna equal to the Jacobian, maybe curl x by curl theta 1, curl x by curl theta 2, until maybe theta, no. Wait, I'm sorry. Not until. It should be by curl theta 1 only. Sorry. By curl x, curl y, and curl z by curl theta 1. For the first Jacobian, for the linear position, it only curl by theta 1 and multiply by the joint velocity at theta 1. And we have by theta 2 until joint n, until joint n. And how can we name this thing? We have velocity vector. We have velocity vector. Velocity vector is formed by the Jacobian of the translation linear 1 and q1 dot. Q1 dot is the joint velocity of the first joint, and we have until Jacobian of linear. Jacobian of linear. Linear means the endpoint velocity. And we know that the joint can be level root joint, or the joint can be prismatic joint. For this joint, we rotate. For this joint, we extend the length, or we change the joint offset. So as I mentioned before, this joint variable depends on the type of the joint, whether it's gonna be prismatic or level root. For the prismatic joint, this one create the velocity at the endpoint. This one, the Jacobian linear that relate to joint 1 multiplied by the joint variable, joint velocity of joint 1. It's gonna create the velocity at the endpoint. So for any joint I, for prismatic joint, the effect in the endpoint velocity, come from the offset, the time derivative of the offset of that joint, and the direction is described by the unit vector. It means that the effect of one prismatic joint depend on the velocity of that prismatic joint, the velocity of that prismatic joint di dot, and the direction of that prismatic joint. The direction of that prismatic joint is described by the unit vector. The unit vector B. So B is unit vector of the axis z I minus 1. Why it should be I minus 1, not I? If you remember from our Denavit-Hartenberg notation, from the notation, d I and velocity di dot is the offset, and the offset velocity along the axis ci minus 1. So from the Denavit-Hartenberg notation, the velocity of the prismatic and the link offset is measured along ci minus 1. So the unit vector here, the unit vector is 3 by 1 vector with the magnitude of 1, and we have 3 components in here that specify the orientation of the prismatic. Jacobian is a vector that relates the joint variable to the endpoint velocity. Jacobian L relate the joint variable to the endpoint velocity. So by the physical meaning here, for the prismatic joint, we have prismatic velocity multiplied by the unit vector that show the direction of the prismatic. So can you guess? I mean, what is a Jacobian? JL1, JLI for the prismatic joint. What is the Jacobian of this? We will summary. How about the Leibniz joint? For Leibniz joint, we need to know omega. No, I'm sorry, not need to know omega. For the Leibniz joint, we also want to compose the linear, because now we are talking about the velocity. The linear Jacobian that correspond to Leibniz joint, the linear Jacobian that respond to Leibniz joint. If we see this picture, the endpoint velocity, if we need to relate to the Leibniz joint, the velocity at this point, when we consider the rotation about this joint, the important factor is the position vector. that lie between the omega to the endpoint position. Omega of joint I, omega vector of joint I, omega vector of joint I have the magnitude theta dot of joint I and multiply by the position vector, the unit vector that indicate the direction, the unit vector that indicate the direction of that joint, and the unit vector point to the C, I mean the C axis. Yeah, be careful in this picture. In this picture, be careful. This and this are not equal. Okay. For this one, we consider the joint as prismatic. For this one, we consider joint as revolute, just to describe the concept. But yeah, these are not equal in the direction. Okay, for the unit vector of bi minus 1. For the prismatic axis is put in this way. For the revolute, the axis is put in this way. But by meaning, omega of the joint I, the omega vector of joint I is described by the magnitude of angular velocity multiplied by the unit vector, But to create the endpoint velocity, endpoint velocity is omega cross r, omega vector cross r, and r is the vector measured from the axis I minus 1 to the endpoint, So omega has the magnitude and direction. So if we consider the cross product, we need to obtain the cross product of the dimension between the unit vector and the position vector. Then multiply by the magnitude of the joint speed, joint velocity. And here is the cross product vector. So in this slide, I think you can understand what is Jacobian, what is the component. We are almost know how to obtain the component of this. Because we know the joint variable, it can be the prismatic or it can be the revolute. But in this slide, what is still not clear is what is the unit vector. How can we compose the unit vector of the axis I minus 1 And how can we compose this relative position vector in the real robot? How can we compose this? So I will let you know. But now we just talk about the velocity at the endpoint. We still didn't talk about the orientation or the angular velocity at the endpoint. So similarly, I'm gonna write down this again, but take this component instead. So for the angular velocity, omega, for the angular velocity at the endpoint as a vector, we need to consider the Jacobian of the angular rotation and multiply by the joy velocity, joy 1, until joy n, until joy n. So for prismatic, the J, A, I, or the Jacobian that relate the joy velocity to the endpoint angular velocity of prismatic multiply by the joy velocity, joy I velocity. Do you think the prismatic joy can create any angular velocity at the endpoint or not? Do you think the speed in the prismatic joy can affect the angular velocity at the endpoint or not, in your opinion? The prismatic joy not rotate the things, and it doesn't change any component in the omega vector at the endpoint. So for prismatic, it's zero vector. For the Jacobian of the prismatic, here it will be zero vector if the joy for prismatic for level joy Jacobian that relate the angular velocity to the joy velocity. We are not talking about the velocity, the translation velocity. We're talking about the angular velocity. So it's straightforwardly to relate the joy velocity, the individual joy velocity, to the angular velocity at the endpoint. We have the magnitude of the joy velocity, of level joy velocity, and just multiply by the unit vector. The unit vector. For example, if we have, if we have the omega, the theta dot. For example, if we have theta dot of joy 1 about z-axis, what can we change with the orientation at the endpoint? It's just straightforwardly like this for level joint. So yeah, for position, it may a little more complicated. We need to consider the prismatic velocity and the unit vector of that prismatic. For level is the most complicated one. We need to compose the omega from zeta dot and unit vector bi minus 1. And we need to find the relative position vector that we still don't know what is this vector. This is for the endpoint velocity. But for the angular velocity, endpoint angular velocity is not that much complicated. For prismatic joint, it's just 0 here. The Jacobian is 0 because it doesn't change the orientation. But for the revolute change the orientation straightforwardly. We just need to consider the unit vector of that joint. How can we combine? How can we summarize the things? How can we summarize the thing? Okay, for prismatic, the full Jacobian for linear translation of joint I and for angular velocity of joint I. For prismatic relate the Jacobian relate the joint velocity and the joint velocity and the endpoint velocity. For prismatic, we have the unit vector as the first 3 components in Jacobian for the linear translation. For prismatic, the joint variable is di. The joint variable is joint velocity is di dot, and the Jacobian is just the unit vector of that joint, so that we can relate it to the endpoint velocity. And prismatic doesn't change the orientation, doesn't change the angular velocity at the endpoint, so it's 0 vector. Here is the conclusion for prismatic. How about the revolute? For revolute, the linear and the angular. For revolute joint, the Jacobian is for revolute joint. If we check the endpoint velocity and relate it with the joint variable, we need to multiply the joint variable, the joint speed, with this component, so that we have the velocity at the endpoint. So this component is the Jacobian for position of the revolute joint. We need to have the cross product of the unit vector and the relative position vector that point from the origin of that frame to the endpoint, and the cross product we have like 3×1 vector. And the angular, the rotation, the Jacobian relate the joint speed to the endpoint angular velocity. So only the unit vector of that direction is needed for the Jacobian. So it will be the unit vector. And yeah, it's 3×1 vector. And the total dimension is 6×1, 6×1. Okay, until now, the problem is we're almost going to the end. The problem is, what is the unit vector? And what is the relative position vector? Is a function of the joint displacement. These are function of Q1, Q2 until Qn. It depends on the joint displacement. If we want to obtain this, it depends on the joint displacement of each joint. It's not a fixed, it's not a constant. It depends on the position of the joint, the displacement of the joint. So we first think about we're gonna define the vector B. Vector B is 0, 0, 1. With respect to the frame I-1. Vector B, if we consider just the frame I-1, vector B lies in the z-axis of the frame I-1. So the unit vector that we want to find here, can be obtained just only from the rotation metric. Of 1 with respect to 0, and we rotate with the joint angle 1 until the rotation metric of joint I with respect to I-2, the rotation metric, and angle will measure until joint I-1, and we obtain the rotation metric, and this product of the rotation metric from joint 0 to the frame I-1, we have 3×3 metric, right? But the unit vector need to be 3×1 vector. So we multiply it with B bar, so that we only get the C component from the product of the metric, of the rotation metric, and we only need the C component. And we have the unit vector, the direction of the unit vector for the joint. How about the relative position vector? The relative position vector. From the homogeneous transform, we have 4x4 metric. So in this case, we compose the 4x4 metric. And yeah, we want to obtain the relative position vector, but we obtain it from 4x4 metric that show the relative position between the endpoint with respect to the frame I-1 origin. And how can we obtain it? The idea is we obtain the endpoint position. Endpoint position obtained from the homogeneous transform 1 respect to 0, joint 1, until n minus 1, and the joint n. And the x bar for this we have I that show the z axis. For this, we are compose the things that relate to the origin point of the frame. Origin has 0, 0, 0 position in the frame, and it's 4x4 metric operation. If you remember, in the homogeneous transform, we have this, the 1 as one component, the last one from the 4x4 metric. So this x bar is this one. This relates to the position of the endpoint, but we want to obtain the relative position vector. So when we already obtain the position of the endpoint, we need to subtract by the position from the base to the joint I-1. It means that if we want to obtain this vector, we need to know the position here and know the position here. And yes, this is the method to obtain that. The position at the endpoint, the origin of the frame at the endpoint, subtract by origin of the frame at the frame I-1. So the relative position vector from this, what we have, we're gonna have the 4x4 metric, right? But yeah, if we multiply the 4x4 metric with x, we're gonna have 4 by 1 because it's 4 by 4 and 4 by 1, and finally we have 4 by 1. Yes, the total dimension of this product will be 4 by 1, but the relative position vector should be 3 by 1. So yeah, we just pick the first 3 components here to be the relative position vector, because the last component, of course, the value will be 1. And yeah, here is the idea. How can we find the unit vector and the relative position vector? And next week, we will give one example of robot manipulator, and we will try to use this idea to obtain the Jacobian for the linear velocity and Jacobian for the angular velocity at the endpoint for one example of robot. So yes, that's all for today. Thank you for still staying together. I have the record for the class. So what I need to do is I'm gonna send you the record to the class. We have 2 parts. We have the lecture on the second half, and we have the talk about the Arduino program in the first half. And I will hurriedly check your design and prepare the 3D part for you and plan to ship it to you on next Monday. If you can come to pick, it will faster, but yeah, consider safety. Maybe just send me your address, I will ship it to you. But you need to tell me about, do you have some screw in the box set for the turtle bot? If you don't have, I will put you some screw in the box. Thank you very much.